Welcome to the session Development of Vehicle Model in MATLAB Simulation. In this session, we will develop the mathematical model of vehicle by solving the differential equation with the help of MATLAB Simulation. If you already about the using of MATLAB Simulation for solving the differential equation, then it's fine. Otherwise, we will also go step by step procedure for this particular example of vehicle model. We have already discussed about the dynamic equation of vehicle, and in this session we will use the MATLAB simulation for developing the mathematical model. We will use this equation. The applied force is equal to ma, that is m into dv by dt, v is the velocity, plus opposing force of aerodynamic drag. So this opposing force and plus, if it is vehicle is at incline angle beta, then the component of gravitational force is mg sin beta. So these three forces are opposing the supply force, and it will result in equilibrium speed for applying force. So it will determine the steady state speed and also give us the idea about the response, how fast or slow we will achieve the steady state speed for the applied force. So this is the system level simulation. Here our main input parameters are weight and inertia of the vehicle and supplied force. So this is called the system simulation because we use the generally system simulation to represent the mechanical, electrical or even magnetic or chemical system. Next hierarchy in the simulation level is the unit level simulation, where we use the in-depth simulation of different unit like the motor, converter, then engine or chassis and different segments level simulation, and then we join this all simulation together. This is next step. We are not going to discuss that unit level, and furthermore for the higher prediction and to predict the more information, we use the component level simulation of MOSFET, simulation of joint, and then we merge together. So because this is the multidisciplinary course, we use the first system level simulation. Here we are designing the simulation of vehicle, simulation model of vehicle. So this differential equation will be simulated in the MATLAB. If we use this equation, so ma or m dv by dt is equal to supplied force, applied force minus fd is the aerodynamic drag force and minus mg sin beta. So this can be easily simulated with the help of Simulink library of MATLAB. Let's see. Here is the model I have developed for the vehicle. So we can see the Fd, applied force, and component mg sin beta. So if you recall this equation at this summation point, so we are having the equation m into dv by dt is equal to supplied force F, that is force we applied, opposing force represented by minus sign Fd and mg sin beta. So opposing force are Fd and mg sin beta. So we are having m dv by dt is equal to F minus Fd and minus mg sin beta. So we will see what this Fd and what is mg sin beta, but at this summing point first we need to realize the equation that we discussed is realized at this summing point. M dv by dt is equal to F minus Fd minus mg sin beta. Now in itself equation of Fd, sometime we use the negative sign to represent it is opposite to the direction of velocity. But to understand, by assuming the direction of velocity in the positive direction, it will oppose, so here negative sign will appear. So after this summing point, if we move forward, then if we want to integrate it, and before if we want to divide by the mass with the gain block, you can find the gain block in commonly used block. Here gain you can drag it, and this gain block you can set whatever gain you want. So for more clarity, I have written in the same format 1 by 200, 200 is the mass. So here we have assumed the vehicle mass is 200 kg, and if we divide this m dv by dt by 200, so what will remain at this side? So we will have dv by dt. So here we are having dv by dt. Now if we use the integration of dv by dt, then integration block will be used, that also we can find here, and this integrator block we can use. So integrator is used so that at the end of integrator output will be Vx. So integration of dv by dt is Vx. So what we want the predict if we apply the certain amount of force, what will be the speed. Here force is also constant steady state, but in actual speed it will be, in actual performance it will be vary. We will see later how we can do this, but this is the vehicle simulation, we can do this. For the applied force, what will be the speed? Here speed will be in meter per second, and if you remember the equation of FD, aerodynamic drag force, then we are having the several component: frontal area coefficient, drag coefficient, mass density of air, and this is for 1 by 2 multiplied by 0.5. So 1 by 2 the frontal area A, drag coefficient CD, and mass density of air rho. Here we have use the typical values 1.2, 0.4 and 1.2. This is representing 1 by 2 and this is representing the math function. This is square of the velocity. So whatever input, it will be squared and it will remain output. So here we need to use the squared output because we also need to use the sign of velocity, so that if velocity is reversed, the direction of force Fd should also reverse. But because here we are not going to reverse the direction or applying the negative force, so for the moment we can let it only the math function as a square. You can find the math function from the Simulink library and math operator. You can find this math function, and if you open this parameter, you can select the function you want and magnitude square that can be used. So input magnitude will be squared and this squared will be your output at this terminal. So you can see this equation of Fd, V square multiply by 1 by 2 multiply by 1.2 multiply by 0.4 drag coefficient and multiply by frontal area A 1.2. So this is representing the Fd, aerodynamic drag force, that is opposing to the applied force. Now come to this part. This is mg sin beta. So if you go and write the value of m, here we have assumed the mass is 200 kg into 9.81 is the constant. So and beta is currently we can set from here, currently it is set to 0, and sine function we can use from the math operator. So this sine function can be used from the math operator. So this will become beta into sine, so sine beta, and sine beta multiplied by mg. So this will be, this input becomes mg sine beta. So this is our complete simulation model of the vehicle having the weight, mass, and if we are having the radius, then we can also supply the torque instead of force, that we will see. Now to simulate this model, we need to just run it for the particular amount of second. By default it will be 10 seconds in your MATLAB. You need to increase the second because of the high inertia, it will take too much time in physical second. So our vehicle cannot reach to speed at certain km/h in the fraction of second, in 1 second or 2 seconds. So we need to simulate for certain amount of time. Suppose I am setting the 200 second and force, applied force in Newton, it is 100 Newton. So if I simulate, we will see this represent the speed in meter per second and final speed. Let's say is it the steady state speed or not. To check this, we need to check the performance. So you can see it is not showing the exponential plot and this is still increasing, it is not steady state. speed, we need to increase the second. So we will do the two things for refining this data point. We know that this is exponential response, but for the refined you can go to the simulation model configuration parameter, and under the data input export you can see the save option. Under the save option, output option, refined factor, you need to increase the refined factor if your output is not. So when you are using the Simulink model component, not the discrete and not using any electrical sim power system library component, so your simulation will be very fast, but you need to use this refined factor. You can increase to 10, 20, or I use the 50 for refinement. Even if you use the sine function or sine wave, sometime you will find the distortion in waveform. So increase this refined factor and let run it again. So we see this is now our actual response, exponentially response of differential equation, and we can see the steady state speed is 18.63 meter per second. So this is what our vehicle model will give us the exact idea. If we apply the constant force, at this rate speed will increase, and what will be the final steady state speed of the vehicle for the particular amount of force, and we will have also at how much time what will be the speed attained by the vehicle. We can convert it in desired form from the meter per second to kilometer per hour with this gain block. So if you observe speed in kilometer per hour, we will have the around 65, you can see around 67 kilometer per hour is the final speed, maximum speed, steady state speed. And this is the wheel RPM. We can say wheel RPM also by considering the gear ratio 1, or we can say the gearless drive. So 638 RPM. So you can see revolution per minute. So to convert the minute into second, it is multiplied by 60 because it's revolution per minute. So it will become revolution per second, and one revolution represent the 2 pi r meter. So to represent one revolution, it is divided by 2 pi, 2 into 3.14 into r is the radius that we assume. So it is around 0.279 is around 11 inch wheel. So you can see this is, we are assuming the moped or such kind of vehicle, because motorcycle has the radius around 17 inch of. So we are not so if you are using the model of bike, then accordingly you can set the radius for wheel speed and you can use it. So we will also have the distance covered, because this is the velocity, this is dx by dt. So if you want to know how much distance travel at the end of this time, so we can also see distance travel is around 3000, in between 3000 to 3500 meter. That means 3 to 3.5 kilometer in 200 seconds. So this is all output we will have for this input, and this is called the system level model of the vehicle. Now we can also add the torque component instead of force if we want. So what we need to do, we need to use the gain. So what is the torque? I have added the gain. So it will remain force. If it is torque in Newton meter, so I am changing this to torque. So now it will become torque, and force is equal to torque divided by radius, or we can say torque is equal to force multiplied by radius. So if I use this is 1 by our radius is 0.279. So this is torque, this is force. Now if we apply the 100 Newton meter of torque, then we can see the performance speed is 120, greater than 120. Steady state speed is 127 km per hour. This is in meter per second wheel speed. So you can use the display block for all this also. So you can measure the speed and wheel RPM and distance travel for the applied torque. So this is how we can also increase the inclined angle to observe the performance. So this is how we can simulate the vehicle model with the help of MATLAB blocks. Now what we need to do is you need to store the characteristics by doing the experiment in this simulation model. So that you need to do is, starting from the minimum torque, that is say 5 Newton meter, just simulate it and record the steady state speed in terms of kilometer per hour. Ensure that it is steady state speed, because when you reduce the torque it will take more time to reach the steady state speed. So if it is taking longer than your simulation time, then it may not be steady state speed. So here I need to written it is kilometer per hour, and this is your meter per second. So let's observe it is steady state or not. So you can say this is not steady state speed. So when we are applying the less amount of torque, it will take more time. So let's increase it to 500, so we can have steady state speed. So you can see now it is steady state speed, so it is fine. So what we want to, for the applied torque and measure the speed in kilometer per hour, we will use this table. This is Newton meter. So for the 5, the speed is 28.4. Let's do the experiment one more time, increased by 5. So for the 10 Newton meter torque, steady state speed is 40. So for 10 it is 40.16. Likewise, you need to plot up to the 100 with the increment of 5. So for the 15 it is 49.19. So when you plot this characteristics, torque speed characteristic, it's called the torque speed characteristic of vehicle. We are measuring the steady state speed. We will use this characteristic for merging the different system level simulation, electrical with this mechanical model of the vehicle. So this torque is generated. So do this experiment and share your result of the torque speed characteristic of the vehicle in terms of lookup table as well as in terms of plot. So it will be exponentially increasing. You will realize that it will increase exponentially. So this is called the speed torque characteristic of vehicle, or speed torque response of vehicle, that can be predicted by this model. So this is the output in terms of speed and acceleration performance also we can predict, and distance travel, but main important thing we are interested in maximum speed and the acceleration of the vehicle. And this torque is generated from the electric motor. So in that section of the electric drive, we will discuss about the torque speed characteristic of electrical motor and system level simulation of electric motor that can be generate this torque. And this torque, when applied to the vehicle, we can predict the performance of two systems of combining the electrical as well as the mechanical system. So when we supply the voltage to the electrical system, it will generate the torque that we call say the motor, and this torque is applied to the vehicle model and it will result in speed. So when we supply the voltage, we will get the speed and the performance parameter. So hope you got the basic idea about the system level simulation of vehicle with the help of MATLAB simulation model.